Good afternoon. April 30th, 2023, into April. Cooler, refreshingly. It had already been getting really way too hot. Record highs. Global warming. I used to most worry about global warming, that the Earth was actually falling into the sun and it was an inexorable condition that would lead to everything burning up. But never happened. Since Mine Doomsday didn't happen. Mine Doomsday 2 didn't happen. Mine Doomsday 3 didn't. These kinds of things, of course, just kind of jocularly in a friendly manner. Here's reading Einstein's Out of My Later Years. Albert Einstein begifted us a great last word that he could point to in the middle of his opinions, either way, on the fate of man and the fate of man, with regards to his theories of relativity and his opinions of his desiderata and requirements of a later and future theory for his requirements and desiderata of a model physicist and with regards to such things. And so his book begins with first of all, a self-contained description of the theories of special relativity and general relativity, and as for the original sort of interpretation. So closed in such manner, then also left open in various ways, as has been put in reading from Einstein. And of course, anything is through my own personal lens, and any mistakes are my own, and anything that is not really what he would say that I want to infer from his opinion is my mistake, and it's only from my point of view that I'm only attempting to be sincere and having a generous reading of Einstein that is reflective of, first, the mathematical content, second, the scientific content, and third, exactly what he says, and three, with regards to trying to interpret his impression of things, and that would leave him satisfied with regards to the mathematical and scientific, and the physicists and the model physicists. So that said, I don't know any mistakes reading Einstein. Incompleteness is different, and understanding is underdefined, but here it's a generous reading of a generous, grandiose hedge, and it's very well appreciated and regarded. So after defining special and general relativity and putting that down, and then he defines E equals mc squared and helps explain and relate how energy is a thing, and then he talks about science and space, time, and gravity, about how they're the layers of the fundamental objects, and so it leaves room to explain why mass and charge, the quantities, are different with respect to energy, besides that they have an equivalency. That is the transitions that energy is, vis-a-vis why energy is universal. It's at the same time that there's the complementary fundamental theories of the charge and the kinetic that result, so that it's fundamental again underneath that, but that each of those regimes in their milieus then is about the weak forces and the nuclear forces have this is kind of a tripos or about matter and charge and otherwise energy and their equivalency. And so there's discussed the mathematical background of that and the derivations and the assumptions and vis-a-vis the L principle and this and that. And then Einstein really gets into describing for his total field theory, after putting up his philosophy of science and philosophizing and saying, hey, if physics belongs to philosophy, it's objects of reason, then we have to be sure to make a careful world for our model physicists to not have to rely on our philosophy to have their physics. That is nice. And then he gets into more of his desiderata and requirements of his total field theory, because at this point in time he basically gets into what is local. He says, all right, my relativity theory has that motion is relative. There's no absolute motion. There's no privileged rest frame. There's no privileged frame, but space-time is still absolute. It's total. It's field theory. And it's very, very cool to read of some of the ways he helps delineate what would be possible interpretations after his mathematical theory without much further ado, because people would have some preconceived notions or make some false inferences, that it's pretty cool that it helps to separate Einstein's theory from the larger world's understanding of Einstein's theory, or lack thereof. And so that's pretty interesting, and especially it's rewarding that when we get into a couple of the very, very key touchstones of Einstein, like dice rolling. He's like, well, somebody's got to do it, but he can't be constantly doing it, because that would be work, and the principle of least action would not be satisfied. Or there's no spooky action at a distance, it must be real somehow. There's determinism for these things, and now I'm calling SR, special relativity, space local. And he defines a space and for the space, and says the space here is made of relative space, but it still lives in the outside absolute space. And then he defends Newton and generously, just to make sure that someone could look at that, if that's as far as they got, and say, that's generous, and it reflects that he, as a grandiose hedge, he wasn't a monomaniacal hedge, or a irrational, having reached the irrational state of grandiosis, or being monomaniacal of the crank. That instead he's a fair scientist and a fair philosopher about this fair practice of physics in his mathematics, that he establishes is interchangeable, meaning exchangeable, for anybody, because he's a great grandiose hedge and highly admired. So Einstein then gets into his theory about the space, and then he has his fundamentally his staking out the principles of classical physics, and he says we're dealing with Cartesian space. It's got a norm, and it's about the Laplacian, because that up in the second order reduces down to this nilpotent, and so we're trying to figure out how that can be, and that's what's going on with all manners of harmonic function theory, as I kind of detailed a bit about how the theory of potentials of today, that some people call the theory of potentials just harmonic function theory, but that's only because everything's built up after the metric from the Laplacian, and as a back out over ds squared, or d, where d is d squared dx squared, or with regards to the three variables of the orthonormal vector basis of the space of Descartes in the Euclidean. That's not a unique system. That this principal component analysis basically reflects that there's some cases where the gradient is best reflected by the sum of the partials, and after their square and their root, coming back out of that is this, the harmonic means and this kind of stuff, root mean square. But there's also that gradient can be defined as finding the principal components, what result that there's more of a free analysis with respect to a given orthonormal vector basis, that there's another one that reflects that it's minimized its partial terms except in one dimension, and that basically captures most of the detail in a lot of these cases that would otherwise become singular, and about how that's attached to the spaces everywhere, and as it goes along in the geodesy, coming and going from where it is at state, that is what Einstein left as a ledge in his hedge, so that someone could find a place to rest their foot on trying to gain this edifice and not fall on the precipice of otherwise free theory. So that's been kind of interesting. And we got up to where he was laying out his concept. Then we get back to the end of this section was the centrifugal versus the centripetal. Because we learned about what centrifugal force is, because anything that's spun around and thus on the outside develops force is called centrifugal force. But then later we learned it's like, we can't call it that, because it's got to be centripetal force, because if we add it up this way and that way, and then outside from around the surrounds, it would add up wrong. And so Einstein talked about the Pale experiment. So before I read that, this is the last, this begins another continuation, because there's several pages after this still in this section 2, which is the classical. of this long book or chapter out of my later years called Physics and Reality. So from physics and reality in the part stratification of the scientific system, after that's just part of section 1. After section 2, mechanics and the attempts to base all physics upon it, and this discussion of the Laplacian and discussion of his space, his rigid space, the rigid continuation of a body, the infinite space determined by it, a body of relation, solids, geometry, concept of space, and Galileo and Descartes, and after the Greeks, the Euclidean, and the Laplacian, which is what it sits on that. The central importance of Euclidean geometry, the concept of space is true useful but not indispensable for geometry proper, explaining that there is geometry and geometry of a sort in terms of motion and including the rotational, that's the singular, with regards to otherwise what's only the linear, and vice versa in a sense, with regards to slide and something like a ski jump or something like that, and minima and maxima and related rates and this and that and and methods and available methods in the linear curriculum and the standard curriculum and the nonlinear aspects of the higher order and highly nonlinear and what's called dynamics that develops. So he discusses the lack of definiteness from the point of view of empirical importance. That here's the notion of time in classical mechanics was veiled by the axiomatic representation of space and time as things given independently of our senses. So he's describing that as a false dichotomy of sorts between fundamental and non-fundamental, about this quasi, the pseudo-differential, the quasi-invariant, and these kinds of things. That then he reads off these classical concepts, the laws of force, the law of motion, the law of inertia, and he indicates the laws, plural, of force, and so it represents this as an exchange in terms of the motive force, and so on. So then this section that we left off is the forces must in the first place only obey the law of equality of action and reaction in order that a system of points permanently connected to each other may behave like one material point. And so in this manner he's describing that for a continuum mechanics of things in the infinitely divisible, that still you can treat anything like an object sense. Einstein continues, these fundamental laws motion and mechanics, fundamental laws of mechanics, together with Newton's law for gravitational force, form the basis of the mechanics of celestial bodies. In this mechanics of Newton, and in contrast to the above conceptions of space derived from rigid bodies, the space being sub naught enters in a form which contains a new idea. It is not for every B naught that validity is required for a given law of force by B and C, which is the law of inertia and the law of motion, which is nice because we can set up that a system can be open and restitutive in the external in time that makes for rest exchange momentum. Rest exchange. It is not for every B naught that validity is required for a given law of force by B and C, but only for a B naught in the appropriate condition of motion, inertial system. So going back, he introduced the inertial system a long ways back in the part of his abstraction about the rest frames for general relativity. And it's really that an inertial system represents a frame and represents an independent space here in its concept. And so insofar as the contents of that frame are rotating, that represents yet, with regards to interactions, that essentially is spherical surrounds of this inertial system of frames. On account of this fact, the coordinate space acquired an independent physical property which is not contained in the purely geometrical notion of space, a circumstance which gave Newton considerable food for thought. Pale experiment. Footnote 2. This defect of the theory could only be eliminated by such a formulation of mechanics as would command validity for all be not. This is one of the steps which led to the general theory of relativity. A second defect, also eliminated only by the introduction of the general theory of relativity, lies in the fact that there is no reason given by mechanics itself for the equality of the gravitational and inertial mass of the material point. He is making it free what mechanism arrives at the derivation of inverse square and such with regards to that. Here, that's the sum of potentials and a fall gravity. But he's saying that relativistic effects are still included. And from my point of view, it seems kind of like that space contraction applies in the rotational more in terms of the space, because linear space and space contraction carries out, and rotational space and space contraction carries in. So that's fine. Einstein continues, classical mechanics is only a general scheme. It's very general and quite valid, and for certain things enables post measurements, certain very usual things in any matter of range finding free at a given point in time, relatively to others. It's only a general scheme. It becomes a theory only by explicit indication of the force laws, actions and reactions between material points, as was done so very successfully by Newton for celestial mechanics. Now we might point to all who were there before Newton, that if Euclid was a panel of geometers, that Newton's kind of a grab bag of scientific progress, and that there's the Galilean and the Galilean principle of invariance and all this stuff that had his thing about free fall and what, with regards to that, kind of like Newton or Einstein is like general and special relativity together for a quite unified and holistic thing, that Newton's various things are split apart and separated, like calculus and laws of motion, separate. Gravity, separate. Whereas special and general relativity have kind of been framed together. And then that here it's that SR is local and GR is total. From the point of view of the aim of the greatest logical simplicity of the foundations, this theoretical method is deficient insofar as the laws of force cannot be obtained by logical and formal considerations, so that their choice is a priori to a large extent arbitrary. It's what works out in a sense. It's the inner product of an outer product that results force equals mass times acceleration. That it works out that whatever the velocity resulted, that's what the force was, and it resulted such acceleration with measurement of time. Metrology is quite a field. Also, Newton's gravitation law of force is distinguished from other conceivable laws of force exclusively by its success. And its simplicity. The theory of potentials is not simple. It's saying, well, there's an infinite outside and it falls in and makes this classical and our finite inside. Well, that's quite an outer product to get back to an inner product. And it's like, well, yeah, so foundationally, fundamentally, it's kind of so, but it's kind of intractable. We need all kinds of mathematics of large numbers to understand what goes on out in Cantor space, or the zeros and ones of the entire infinite universe, from our simple orthogonal vector basis of the Cartesian and a perspective for perspective. And so its success is largely its tractability after its fungibility because of its sensibility, because the theory of potentials is after other overarching fundamental concerns is sensible, in fact rather automatic in a sense, whereas that it becomes fungible not so easily, and it says of all these other matters things. Just like the discretization and the quantization is really as of, well, we're trying to measure things that are arbitrarily small, and we need to have finite quantities and things that work up that we can have this spectroscopy and some lines in the spectrum, or these regions and their flows of the utterly and fundamentally small and a unit of aggregation, about the continuum mechanics and the quantum mechanics. So when Einstein says also Newton's gravitation law of force is distinguished from other conceivable laws of force exclusively by its success, that he encompasses that, I imagine, in success. Reproducibility experiment, sensibility, fungibility, and tractability, relayability, freedom from other concerns, all this kind of stuff that goes into, otherwise the questions of foundations do not care. They're insensate with regards to this philosophizing about it, that it's still the mechanism what results so real. So Einstein says, in spite of the fact that today we know positively that classical mechanics fails as a foundation dominating all physics, it still occupies the center of all our thinking in physics. It does occupy the center. We live in the milieu. We live in the middle. We live in the mesoscale from the fundamentally small and the fundamentally large. We live in the middle of our objective perceptions of reality and our subjective perceptions of reality. At the same time, any thinking person can imagine themselves as the center of the universe. Any abstract person has the entire power of foundations to center themselves in the universe, and as well to center it in themselves. That results for this outside and inside, what's to make for a usual sort of complementary dual that makes it so that when Einstein says it occupies the center of all our thinking, that is, we want to result back at that again. All this classical should just result from the superclassical. Superwave motion, the tachyonic, and gravitational fall gravity is gravific instead of gravitic, so as a true centrifugal instead of the centripetal, or the Pale experiment. All these things that end up being classical on the inside, that the object in the universe is everything that it is not. If we were just constantly vacillate between the two, it's the same thing. These are the kinds of things that get into our notions of foundations for mathematics also, in the entire Euclidean space, in the infinity, in the infinitesimals. All this stuff centers itself very well with this sorts of original analysis. And so Einstein is definitely fair to appreciate that it's the same for everybody, and it reflects usual notions like that the laws of physics are the same everywhere. That's a simple inference from the existence of the scientific method and the existence of a universe and the closure of it all. And that's the whole point of if there's the existence of a thing, because otherwise it would just be saying that there's that there's abstract subjectivity, which is fundamentally non-scientific. So if not proven, it's yet abated that what the higher outside could really be in terms of the celestial and in terms of the theological and that has its own space anyways. But for science and a model physicist and a model man, Einstein is Einstein's model physicist has freedom of religion, I guess is what it says. But everyone agrees that anything that's super classical must result in classical on the inside. All right. So the reason for this lies in the fact that regardless of important progress reached since the time of Newton, we have not yet arrived at a new foundation of physics concerning which we may be certain that the whole complexity of investigative phenomena and of partial theoretical systems of a successful kind could be deduced logically from it. In the following lines, I shall try to describe briefly how the matter stands. So this, for me, is a great and a wonderful insight of Einstein's, that there's following some kind of axiomless natural deduction, the ability to consider something like a mathematical universe hypothesis, and that the partial theoretical systems of a successful kind could be deduced logically from it, as he puts it. I find that incredibly compelling. That's one of my greatest desiderata and requirements of a theory of foundations, is that first I need a geometry that arises naturally, and then a science after statistics that arises naturally, and then a physics that more or less is discovered, not invented. Then theories are invented to attain to that, these partial theoretical systems of a successful kind, for all the investigated phenomena and their whole complexity. Well, what does he say? That he says, first we try to get clearly in our minds how far the system of classical mechanics has shown itself adequate to serve as a basis for the whole of physics. Since we are dealing here only with the foundations of physics and with its development, we need not concern ourselves with a purely formal process of mechanics. And he indicates some examples. Equation of Lagrange. This is any time-like system about what makes the Hamiltonians, which result these tensorial products, or for a bracket in the quantum, and it's parameterized by T. Canonical equations. These, for example, are the classical equations. Still, that though scientifically they're not falsified, so we got to figure out how those add up, etc. One remark, however, emphasis on the author on one remark, however, appears indispensable. The notion material point is fundamental for mechanics. Well, that's the degenerate element of a space, is a point. And so he might as well have said the notion material space is fundamental for mechanics. It's a continuum mechanics. If now we seek the mechanics of a bodily object which itself cannot be treated as a material point, and strictly speaking every object perceptible to our senses is of this category, then the question arises, how shall we imagine the object to be built up out of material points, and what forces must we assume as acting between them? The formulation of this question is indispensable if mechanics is to pretend to describe the object completely. Emphasis authors, completely. It's a continuum mechanics, as usual notion of that there's discretization and quantization, and the formulation of the question is indispensable. And then the forces we assume to act in them are zero. The principle of least action is that there's no free work. There's anything that's contrived, like enthalpy, can be an opposite of entropy. Entropy can be the reverse of its usual meaning in usual systems that involve any kind of anisochronism or anisotropism, where there's no anisochronism, but there are these relative effects, and anisotropism represents an organization or a closed system for open system of physics. The formulation of this question is indispensable. Question: how shall we imagine the object to be built up out of material points, and what forces must we assume as acting between them? The idea of this fall gravity is unifying the strong nuclear force is that, and I'm still not quite sure how to explain how the protons don't repel each other. But the strong nuclear force is so strong that it so perfectly balances the repulsion of charge that the protons sit together, but it could be that there's just the atomic number is a quantity and mass is conserved, that the integrity of the atomic is conserved somehow for the nuclear force as applied to the otherwise a strong nuclear force, or in this. That what I'd wonder then is when Salam and Weinberg in the 1970s, in their subatomic physics, they are part of what's also called quark physics. And so inside the atomic nucleus are protons and neutrons in our most usual model. There's not a billiard ball model, there's not a pudding model. There is a model of electron orbitals that, according to a dense inner nucleus, that the atom's volume is mostly space, and that the electron orbital theory, in accords with all the other theories that build this up, have that inside the nucleus is protons and neutrons, and so it results that there's a hypothetical particle called the free hydrogen ion with one atomic mass unit, that then there's this that the nucleus has subatomic components, proton and neutron, that the proton and neutron have subatomic components, and in the world of particle physics, the entire zoo is only full of particles. Everything in the particle world is a particle that is made up of quarks, and they're connected as by gluons, and then this is called quantum chromodynamics for the color forces, what result in high energy experiments of the atom shattering. That these are the model forces that represent the internal binding energies of these things. And so what Weinberg and Slom discovered was that inside the atom, all the way on the inside, it's asymptotic freedom. And so asymptotic freedom is this entirely concept of that, how could it be that all the way in the middle it's loose instead of most dense? Well, this is the idea that this fall gravity unifies with this strong nuclear force, that it results that it's just configuration and organization in a body, that this point is it's just refinements of individuation of a continuum. They're individua of a continua to be a point. And so when you look at quantum chromodynamics, it's like, well, now we've broken down protons and neutrons to this table of quarks. Then there's this theory called technicolor, and it's that quarks have quarks have quarks have quarks all the way ad infinitum, that there's no the smallest particle that it breaks down. Then the other idea to keep in mind in terms of the space of things is in that, first of all, that bodies are mostly treated as by their surfaces which contain them. And there's something like Israel Ashfle's book on surface forces, that is a key thing with respect to how things really are empirically, with respect to the atomic models of things and the boundaries of things. So anyways, underneath atoms, which are 25 order degrees of magnitude small, is superstrings are 50 small. And then whether they're open or closed is basically whether they're in a line or on a line. And what that demands for mathematics is continuum mechanics for mathematics. And how that's defined is in terms of infinities and infinitesimals. And one of the great things that makes Einstein's work all success is there are none, because they become mathematically ambiguous and mathematically intractable. But the point is essentially a degenerate interval with analytical character that in its summation over all its neighbors, which so defined by the partitioning of such a region, by all these boundaries down to none, equals 1. Or 1 over infinity equals 0, but here that's where infinity over infinity equals 1. Specific. The formulation of this question is indispensable. Mathematics owes physics this, if mechanics is to pretend to describe the object completely. It is natural to the tendency of mechanics to assume these material points and the laws of force acting between them as invariable, since time alterations would lie outside of the scope of mechanical explanation. It could be contrived in like two black holes. There could be a black hole and then a black hole within it that would essentially have copies of contents, and one would go one way and one the other, but not that they could ever come back, and not that they could ever, have closed time-like curves. Time travel is utterly contrived, and if there's time travel, it means you're living in a bubble. It's not a thing. Since time alterations would lie outside of the scope of mechanical explanation. From this we can see that classical mechanics must lead us to an atomistic construction of matter. It does it for the chemical and elements after the experimental science, what was called alchemy, after the original elements of fire, water, earth, and air. What results in things like the discovery of oxygen, and that in a closed volume the mass stays the same, and this kind of thing. That the atomistic, after Democritus was a scientist who developed this theory of atomism, the uncuttable, that substances are made up of things and an infinity of them. It makes a continuum of them. This individuation of the individua of the continua points in a line, or points on a line. Classical mechanics must lead us to an atomistic construction of matter. These days, that goes all the way to the Planck regime, which is 5 or 10 orders of magnitude smaller than the atom, and then for superstring theory, all the way down twice as many orders of magnitude to make a smooth background for the grain of atomism, because it's continuum mechanics. And then the massive protons and the massive electrons and the lifetime thereof of protons and electrons, which otherwise are deemed infinite, and that mass cannot be destroyed, although there is mass energy conversion of a sort with the antimatter. But anyways, that this is our atomistic theory because it's a continuum mechanics, and it's only sensible and fungible and tractable largely as particle mechanics and of the finite. There are, though, entire bodies of work, and it's called real analysis, about essentially matters of the infinite. And then there's entire bodies of work, and they're becoming a long way, like Ramsey theory, the quasi-invariant, the pseudo-differential, Jordan measure, and the Dirichlet problem, which reflect for notions like field continuity, line continuity, and signal continuity, besides what we have, what are called our continuous functions, and our classical functions, and continuous functions that are real functions, that there are these not real functions that still have analytical character well defined, and that there are these continuous domains which involve the foundations of mathematics. So he's saying that mathematics owes physics continuum mechanics fundamentals. It is natural, From this we can see atomistic of matter. We now realize with special clarity how much in error are those theorists who believe that theory comes inductively from experience. I don't understand. Even the great Newton could not free himself from this error. Hypotheses non fingo. There's a note, he says, I make no hypotheses. That is one. In order to save itself from becoming hopelessly lost in this line of thought, atomistic, science proceeded first in the following manner. The mechanics of a system is determined if its potential energy is given as a function of its configuration. So this refers to the configuration space, the configuration of experiment, the energy of experiment, reflecting the regimes of the spaces of the quantities in the experiment. The mechanics of a system is determined if its potential energy is given as a function of its configuration. Now, if the acting forces are of such a kind as to guarantee maintenance of certain qualities of order of the system's configuration, then the configuration may be described with sufficient accuracy by a relatively small number of configuration variables, Q sub r. These are usually represents the momentum operators of the quantum physics. The potential energy is considered only insofar as it is dependent upon these variables. For instance, descriptions of the configuration of a practically rigid body by 6 variables. Here he alludes to, which he would certainly have been aware of Bowman de Broglie and their quantum mechanics, and the hidden variables that are variables that represent any matter of non-locality. But here he's just saying is that it's successful if it's easier to compute, and that's so. And it's only possible to make a reproducible experiment in some of these configurations, and what can be made symbolic and what can be made well-defined, well-behaved, and what computes. So he's then expressing that by a relatively small number of configuration variables that those accurately parameterize the models that results in parametrization of the theory of some potentials, or theory of omega potentials, or theory omega that adds it all up. A second method of application of mechanics, which avoids the consideration of a subdivision of matter down to real material points, is the mechanics of so-called continuous media. So these are surfaces, and the values and quantities are flows. This mechanics is characterized by the fiction that the density of matter and speed of matter is dependent in a continuous manner upon coordinates and time, and that the part of the interactions not explicitly given can be considered as surface forces, pressure forces, which again are continuous functions of location. Herein we find the hydrodynamic theory and the theory of elasticity of solid bodies. You know, hydrodynamics is fluid mechanics, and there are more of them because there are lots of things that have partial fluid models. And then the theory of elasticity of solid bodies and their deformability and learn is all the stuff of crystallography. We read a lot of that from that nonlinear electromechanical effects and applications from Morgan. And then these theories avoid the explicit introduction of material points by fictions, which, in the light of the foundation of classical mechanics, can only have an approximate significance, or they're relevant in their domain, or they effectively close certain otherwise symbolic representations that, given that they can be built from these fundamentals atomistically, that the fundamental is truly fundamental and elementary, that these are the kinds of things that go into these applications. Whereas, well, what results something like force, and the definitions of force is exactly in this milieu, compared to scattering and tunneling theory, which is just things flying about and coming together, forceless, vis-a-vis connections or couplings. So that's kind of where it lives, these quantities, is in this continuous media. It's a continuum mechanics that has all discrete mechanics as a subset of it as a model in a pure theory that's axiomatic set theory or axiomaless set theory. That so is a model of it. Abstractly, by definition, not that there is one, not that it's successful to use it as physics, but there is one, is a thing. These theories avoid the explicit introduction of material points by fictions, which, in light of the foundation of classical mechanics, can only have an approximate significance. In addition to their great practical significance, these categories of science have, by enlargement of the mathematical world of ideas, created those formal auxiliary instruments, partial differential equations, which have been necessary for the subsequent attempts at formulating the total scheme of physics in a manner which is new as compared with that of Newton. These two modes of application of mechanics belong to the so-called phenomenological physics. Phenomenological. It is characteristic of this kind of physics that it makes as much use as possible of concepts which are close to experience, but which, for this reason, have to give up, to a large degree, unity in the foundations. Heat, electricity, and light are described by special variables of state and constants of matter other than the mechanical state, and to determine all these variables in their relative dependence was a rather empirical task. Many contemporaries of Maxwell saw in such a manner of presentation the ultimate aim of physics, which they thought could be obtained purely inductively from experience on account of the relative closeness of the concepts used to the experience. From the point of view of theories of knowledge, St. Mill and Ernst Mach took their stand approximately on this ground. Now I'll have to look into Stuart Mill and Ernst Mach a bit about the empirical, and about what they figured is like, well, we can at least give these classical linear derivations people. When it comes to potential theory and all these things that are higher, that still falls out as a classical solution. So if they don't know that they need to know, then they don't need to know. According to my belief, the greatest achievement of Newton's mechanics lies in the fact that its consistent applications has led beyond this phenomenological representation, particularly in the field of heat phenomena. This occurred in the kinetic theory of gases and in a general way in statistical mechanics. The statistical mechanics has, for example, Einstein boson, Fermi, Podolsky and boson. It has Bose statistics and Fermi statistics, bosons and fermions, these particle obeying these things accordingly to their phase amplitudes by these statistics. There's pair statistics. There's lots that goes on that mathematics owes physics for the fundamental theory of continuous distributions and the discrete that are also related to continuum mechanics. The former connected the equation of state of the ideal gases, viscosity, diffusion, and heat conductivity of gases, and radiometric phenomena of gases. Like, I imagine radiometric phenomena includes luminescence, phospholuminescence. I'm not sure what else that's to intend. The ionizing, the ionic, and gave the logical connection of phenomena which, from the point of view of direct experience, had nothing whatever to do with one another. I think we need to separate direct experience from the non-existence of supermodels, because uh, there's a big difference between playing with the train set and running all the train system in the world or something like that, and that the wheels on the bus go round and round and what. But it's when you have a continuum mechanics that explains these things. If mathematics could just provide this, then Einstein would be like, now I have a direct phenomenological model that I can write down and reproduce, and it would be mine. You know, Einstein wants his own, if it's to be direct, and that's the point of that's the usual point of application of a successful physics, is for that to be so. From the point of view of direct experience, had nothing whatever to do with one another. The latter gave a mechanical interpretation of the thermodynamic ideas and laws, as well as the discovery of the limit of applicability of the notions and laws of the classical theory of heat. This kinetic theory, which surpassed by far the phenomenological physics as regards the logical unity of its foundations, produced moreover definite values for the true magnitudes of atoms and molecules, which resulted from several independent methods and were thus placed beyond the realm of reasonable doubt. Now, these days, we know that there are running constants, and according to higher energy and configurations of experiment, there are running constants. So the discretization and quantization is really modeled as the vanishing in these points. And so vis-a-vis, fundamental physical constants, the mass of an electron, or the mass of a proton, or the charge each one has, is they have the same but opposite charge, or this kind of thing, that it's a matter of configuration of experiment and energy of experiment. And this is familiar, is that the more science has grown, every few years the universe gets bigger, not just more accurately measured, but bigger according to measurements, and particles get smaller. And that's verified out to about 29 orders of decimal magnitude. The latter gives a mechanical. This kinetic theory, which surpassed by far, and thus placed beyond the realm of reasonable doubt. This was then given as methods to engineers because they could use it in all their classical milieu, which is most things. They were going to be okay with that. And when they had to learn that there were other things relevant to their milieu, then that became the specializations in the domains. Vis-a-vis foundations. This kinetic energy, These decisive progresses were paid for by the coordination of atomistic entities to the material points, the constructively speculative character of which entities being obvious. He's saying that it's pretty obviously not well understood. Nobody could hope ever to perceive directly an atom. Here, this is a pretty key thing when we go beyond classical physics to the experimental physics to the high energy experimental physics, that we're basically relying on the configuration of the setup of the experiment, of that we have a detector and this kind of thing is about the milieu, is about the configuration, and he's just making it clear that there is what is above us and there is what is below us, and they're inscrutable except in a sense to our reason, but at the same time our science technology is able to build upon itself the scaffold of the man, these giants like Einstein on the shoulders of Newton, and on down, and these scaffolds of experiment, and these things that allow things to determine what it goes through, and untold iterations of trial and error and experiment in the empirical, like when the space race began, and for lifting via rocketry objects out to a stable Earth's orbit, that there were thousands of attempts to properly configure the from the nacelles to the cones, these things, what resulted empirically verified constructs that also then advise whatever the mathematics had to provide to make that so. And then today we talk about the adiabatic and the non-adiabatic as basically on either side of, well, it's for the empirical, or well, it was for a theoretical. Einstein, as Einstein put it, nobody could hope ever to perceive directly an atom set by thought experiment. Laws concerning variables connected more directly with experimental facts, for example, temperature, pressure, speed, were deduced from the fundamental ideas by means of complicated calculations. In this manner, physics, at least part of it, originally more phenomenologically constructed, was reduced by being founded upon Newton's mechanics for atoms and molecules to a basis further removed from direct experiment but more uniform in character. And you can replace Newton's with Galileo's, and atoms and molecules with aggregate models. So that's this section 2 of Physics and Reality, and it really got into, then he's explaining that our classical it's at least several things, and one is about the notion of force as derived and not fundamental, and the other notion, and this is from the section Mechanics and the attempts to base all physics upon it, and this other bit is in Physics and Reality is chapter 13 of his book. It gets then in the next section is section 3, the field concept. So the field concept is the idea that a universe exists, and then insofar as then we have all these things about how it can be that they come together and that there's one of them. I found this book the other day. It's called The Crime of Galileo, and I'd written before things like Galileo's Daughter, and this is popular print about the life of Galileo Galilei, and he lived in a time when there was great changes in science in the world, and it was after the Dark Ages and after the Middle Ages, but before the Enlightenment, and the times when there were the terrible troubles of like the Spanish Inquisition and the Roman Inquisition and stuff like that. So Galileo Galilei was famous as an experimenter for showing that, two balls dropped the same thing, they were accelerated by the same way, regardless if the one was denser than the other, although obviously, since Eureka in his bathtub, one floats, one doesn't, or how wood floats, ice floats, da-da-da. So anyways, Galileo Galilei then also did some writings. He studied the field. He was a sort of thinker at the time, and he put together some things which, in terms of the Copernican and stuff, got him banned by the Roman Inquisition, which was much gentler than the Spanish Inquisition, and the terrible things that occurred in something like the Spanish Inquisition, with regards to that the Roman Inquisition was, in terms of the aggregation of power and the way things were, and the teachings and what was the media and the propaganda of the time, how those kinds of things were. And so, whereas René Descartes basically very closely allayed himself and also made sure to offer, these people demanded sufficient apologetics to come along with anything that was advanced in terms of the scientific that would in any way at all reduce any kind of utter fundamental bedrock belief, and otherwise this system of belief, which was strongly associated with attachment to monotheism, and that there was its representatives in the earthly matters, in the earthly realm, and that these represented things that were, for man and humanity, the thing that it should be. And so Descartes was able to basically align himself more with that, and so Descartes published a lot more of these things that had the same content that Galileo did, but while Galileo was basically just housebound for a while, and later his work was published, after that had cooled down a lot. And Descartes lived in a region that was not at the time separate in the space and time when people could travel to it, but it was still, far enough away that it was essentially removed. So that's among the reasons why Descartes' successes became that. Otherwise, Galileo's successes would have been stronger and more like Newton. Whereas Newton came later and it was like, this is part of the scientific revolution. This is part of the Enlightenment and rationalism. And so that's why Newton is held up, because Newton was kind of I would say, sort of a pseudo-scientific spook of a sort, and a very jealous, how you might say, thing. But at the same time, from what I understand of his history, you know, he was an experimental physicist, and he did pull together lots of these things. He had many influences, and he had many results to pull together, and especially with regards to the calculus and the definitions of the fluents and fluxions. These are the kinds of things that Einstein says when he says points. He means infinitesimals. He means like Newton's fluxions, like Leibniz's differentials. These are the things. This is what makes our real analysis today, and the integral calculus and the differential calculus and the infinitesimal analysis and the real analysis and the dynamical models, all that analysis. So anyway, this book is kind of interesting. It says The Crime of Galileo, and it's by Giorgio de Santillana. And so I won't speak too much as above it, but I just picked it up the other day. And what it does, it has in its introduction something about Oppenheimer. So when I saw that, I was like, Galileo did not come to grief as the scientist facing a religious credo. He was far from standing the role of a technician of science. Had he done so, he would have escaped all trouble. Everyone knows that his discoveries went unchallenged. Those of Descartes did too. So did Descartes himself, but then, as he admitted it, he went forth under a mask, whereas Galileo was the man without a mask. Both his friends and his enemies saw in him a unique type of creative personality whose essential achievement might very well be conceived to stand or fall with him. He was a classic type of humanist, trying to bring his culture to the awareness of the new scientific ideas, and among the forces that he found in line against him, religious fundamentalism was by no means the strongest. There's always fortune. They say fortune favors the bold, but well, anyways, that's something to just put in some context. So for Einstein, that when it comes to Einstein, he points at Newton, because he knows that after the 20th century and the ubiquitous success of relativity and special relativity separately, and quantum mechanics, everyone points to him, and then to find him. So anyways, we'll get to that some more later. I hope you enjoyed this discussion today. There's enough solar energy that the little globe's been spinning around, and that globe is kind of interesting. It's a map or the globe terrestre is from a time almost before when the globe was known to be that well mapped out, but it's pretty accurate. All right then, hey, have a great day.